The topic for this video is covalent bonding. The essential questions are: how do you draw an electron dot structure for a covalent compound? So we're going to use the rules for Lewis dot structures, and we're going to go through this. The first step, we calculate the number of valence electrons each atom contributes, and we're going to divide this number in half to get the number of pairs. So we're going to use an example as we go through the rules, and we're going to use carbon tetrabromide, so CBr4. Carbon, we know, is valence electrons of 4, and there's only one carbon. Bromine has 7, and there are 4 bromines, so each one gives us 7, so that's a total of 28. So we have 28 from bromine, 4 from carbon, so that gives us 32 electrons we're going to be drawing. And so we're going to divide that number in half to get the number of pairs, so that gives us 16 pairs. The next step is to decide which element will be the center atom. It's usually the one that has fewer atoms or the lower electronegativity. If we look at our example, we have 1 carbon and 4 bromine. Well, these like to be symmetrical, so it makes the most sense to put the carbon in the center. And typically carbon, sulfur, or phosphorus are good bets for the center atom. It's not going to be every time, but chances are those might be the center. So for example, CH4 is going to have C in the middle. SO2 would put S in the middle, PCl5 would put P in the middle, and again, if you look at those, there's one of those and several of the other element involved, so they're going to go in the center to make it as symmetrical as possible. Okay, the next step is to use the pairs of electrons as single covalent bonds to attach all the other atoms to the center atom. So I'm going to put C in the middle, and it's going to bond to a bromine, and that line is going to represent 1 electron pair. And there's another bromine. I have 4 total, and there's another, and there's another. So I've used 4 pairs of electrons there out of my 16. Okay, so then we're going to keep going because I have 12 more pairs to go, and we're going to put lone pairs of electrons on the outside atoms until each has 8 electrons, which is 4 pairs, or if we're dealing with hydrogen, it's just going to be 1 pair. Okay, so if you look at carbon, carbon already has 4 pairs coming off of it, so it's full. Okay, so we're going to add to bromine, though. Each bromine only has 1 pair, and it can have 4. So now that top bromine is full. And now I've used 4 pairs in the center, and then 3 more on the outside of that bromine, so that's 7 pairs, 8 pairs, 9, 10 pairs, 11, 12, 13 pairs, 14, 15, 16 pairs, which is how many I had in the beginning. Okay, if we have any leftover pairs, they're going to go on the center atom so that it also has 4 pairs around it, but as we already talked about, that carbon already was full. If there's not enough pairs to obey the octet rule, then we're going to convert the loned pairs into additional shared pairs, which would mean we have double or triple bonding, and I'll show you an example of that a little bit later. And then we're going to decide what shape the molecule should be. So when I have that carbon has no lone pairs on it and it has 4 on the outside, if we think back to our Vesper theory, 4 molecules on the outside gave us a tetrahedral shape. Okay, now we're going to try some examples. So let's start with water. Hydrogen has 1 valence electrons, and in water there's 2 hydrogen molecules, so that makes 2. Oxygen has 6 valence electrons, so that makes a total of 8. We divide that in half, we get 4 pairs. So between there's 2 hydrogen and 1 oxygen, I know oxygen is going to go into the center to make it symmetrical. And I'm going to attach it to a hydrogen, and I'm going to attach it to my other hydrogen. Okay, so now that's 2 pairs out of 4. So hydrogens are full because they're only allowed to have 1 pair each, but my oxygen can have 4 pairs and it only has 2. So I can put another pair there and another pair there. And if I look at that, if I have 3 atoms with 2 lone pairs on the middle, that's going to make a bent shape. Okay, let's look at another one. PF3. Phosphorus has 5 and there's only 1 of those. Fluorine has 7 and there's 3, so that makes 21. So 5 and 21 give me 26 electrons or 13 pairs. Again, I have 1 phosphorus and 3 fluorine, so it makes sense to put phosphorus in the middle. I'm going to attach it to the fluorines, and there's 3 of them. Okay, So now I've used 3 of my 13 pairs, so I have 10 to go. So I'm going to start around the outside, and those fluorines can have 4 pairs each, and right now they only have 1. So I have 3 pairs. There's 4, 5, 6, 7, 8, 9, 10, 11, 12. But I have 13, so now I'm going to go to the middle. Phosphorus is allowed to have another pair because it only has 3 pairs right now. So I'm going to stick that on there. So now when I start thinking about the shape, okay, if I think about one atom with 3 attached to it and a lone pair, changes the shape a little bit. Okay, it's going to look like that, and that is a pyramidal shape. Okay, now let's look at CO2. Carbon has 4, and there's 1 of those. Oxygen has 6, and there's 2 of those, so it makes 12. So 4 and 12 give us 16 electrons, or 8 pairs. I have 1 carbon and 2 oxygens, so to keep this as symmetrical as possible, carbon's going to go in the middle. I'm going to attach it to oxygen on either side, so that's 2 out of my 8 pairs. So now I'm going to start attaching to my oxygens. I have, let's see, I had 2 pairs going. There's 3 pairs and 4 pairs, 5 pairs, 6 pairs, 7 pairs, 8 pairs, okay? But here's the problem. Carbon only has 2 pairs attached to it, and it needs to have 4. Okay, so I'm going to have to do something about that. So what I can do is pull one of those electron pairs over here in between the carbon and oxygen, and it creates a double bond, and I'm going to do that on both sides. And so what that's going to look like, I'm going to start again. I have my carbon and my oxygens all connected, so there's 2 pairs. That's now double bonded on the left there, so that counts as 4 pairs. I'm sorry, 3 pairs and 4 pairs. Okay, so there's 4 pairs right there. It's double bonded on either side. And I'm going to go back out to my oxygen. My carbon is now taken care of with its 4 pairs. So I have 4 pairs done. There's 5 on the oxygen, 6, 7, 8. Okay, so that's how that double bond thing works. And so if I look at that, I have 3 atoms, and the middle doesn't have any lone pairs on it, so that makes a linear shape. Okay, we're going to do one more. COF2. Carbon has 4, oxygen has 6, fluorine has 7, and there's 2 fluorines, so that makes 14. If I add 14, 6, and 4, I get 24 electrons, or 12 pairs. Okay, now this is a little bit confusing because I have 1 carbon, 1 oxygen, and 2 fluorines. So you could argue that either carbon or oxygen might go in the middle to make it symmetrical. However, if you remember in the beginning, our rule was that carbon's one of our best bets if we're not sure. So let's go ahead and put carbon in the middle. I'm going to attach my 3 atoms, so fluorine, fluorine, and oxygen. Okay, so there's 3 of my 12 pairs. Now I'm going to start going around the outside, so there's 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now everybody has 4 pairs except for carbon. So this is kind of like the last one. We need to figure out a way to fix that. Okay, and what it's going to have to do is share. And it's going to share with oxygen. Again, that's going to make it the most symmetrical. If it shared with 1 fluorine and not the other, that wouldn't really make sense. And so I'm going to move that to be a double bond. So I'm going to still have my bonds with fluorine, 2 fluorines and oxygen, and I add that double bond there. Okay, so now I have 4 of my 12 pairs, and I'm going to add 5, 6, 7, 8, 9, 10, 11, 12. So now there's 12 pairs on there, but everybody also has 4 pairs, which is what we want. If we look at that, we have 3 around 1 atom, and that central atom does not have any lone pairs, so that makes a trigonal planar shape.